Hi everyone, I'm Alexander Moreno, and this is a robust functional EM algorithm for incomplete panel count data. Our goal is to identify temporal patterns of risk factors that may prevent an individual from successfully modifying a health-related behavior. As a subtask, we'd like to model the counting process of a repeated negative event. Here the mean function is particularly helpful and interpretable. The data we look at is called ecological momentary assessment data. Here, behavioral events are recorded via EMAs, and participants respond to prompts and enter data via an app. Our setting involves questions randomly prompted by an app asking, how many cigarettes have you smoked since the last assessment? And this is a type of panel count data. So the mean function describes the expected number of total cigarettes smoked over time. And the challenge in estimating it is that EMA has missingness patterns. So the first setting we consider is an old setting. And here you want to estimate a mean function under this observation scheme where there's no missing data using a Poisson process log likelihood. And we have counts since the last observation time. So it turns out that this was shown how to do 20 years ago in a setting where you're actually robust to Poisson process violations. The second setting involves some intervals being missing, and current methods don't handle intervals with unknown counts. So under a missing completely at random assumption, we would like to also provide theoretical guarantees. So there's three types of missing EMA. The first is EMA is delivered, user doesn't complete. A second is that it's not delivered due to some condition not being satisfied, for instance, driving. The third involves gaps with no information whatsoever. So the high-level algorithm idea is a functional EM algorithm where we wrap existing mean function estimators. In the E step, you use the current estimate, you impute your missing data. In the M step, you call an existing method and estimate a new mean function. Now, we don't always have a ground truth for the missing data, so we need theoretical guarantees. And in more detail, in the E step, we use our current estimate to fill in missing intervals. In the M step, we take the filled in data and use an existing method to estimate a new mean function. So we have two theorems. The first one is convergence of population EM. And what this says is that if you start in some ball around your true mean function, as the number of iterations increases, the ball shrinks. Theorem 2 involves convergence of finite sample EM. And here you still have the original population term, but now you have another term that goes to 0 as your sample size goes to infinity. We also look at a smoking cessation study, and this involves 125 participants over 14 days. We treat intervals over 24 hours as unreliable or missing data, but use the reported for initialization. And we look at how many cigarettes, which is targets 3 to 4 times a day, and long intervals make up 5.7% of observation. And this leads to a 21.7% difference between estimates of total cigarettes when we believe what they say versus when we impute. So to wrap up, we proposed a functional EM algorithm for missing panel count data. We showed finite sample guarantees. We showed results on a smoking cessation study. And this can help us more accurately describe smoking behaviors in the presence of unreliable self-reports.